Good morning, everyone. Thank you very much for joining our first Eupraxia seminar series today. We've got our first speaker, Jorge Vieira from Instituto Superior Técnico, IST, in Lisbon, and he is going to talk to us about achieving superradiant plasma accelerator-based light sources with collective effects. Thanks so much, Jorge.
Thank you, Anna, for the introduction, and thank you also for the kind invitation to give this talk. So the title is relatively long. So during my talk I'm going to describe the three main keywords of this work. So plasma accelerators, light sources, and also collective effects. So before I start, I'd like to acknowledge all my collaborators here from IST and from abroad, also Eupraxia, of course, and the supercomputing tools and supercomputing resources through EuroHPC that we have been using. Okay, so now I'm going to start by providing an overview of plasma accelerators, growing from the experiments and computing that are leading us to the results that we have today. And then I am going to move into plasma accelerator light sources. So I'm going to cover a little bit of the basics and their applications. And this will bring me to the main the main topic of the talk, which is this ultra bright light sources based on collective effects. So a transition from incoherent emission to coherent emission and superradiant emission. And then I'm going to conclude with an outlook and perspectives. Okay, so the main goal of plasma-based accelerators is to make a more compact and hopefully less expensive particle accelerator. So why is this important? So in order to understand why, let's just start looking at this image here. It shows the proton synchrotron. This is a circular accelerator. It was built at CERN in 1959. It has a radius of 100 meters. So after these first successful experiments, it was decided to build a bigger accelerator. So this was called the super proton synchrotron and built in '76. This is again a circular accelerator, but the radius now is 1 kilometer, so 10 times longer than the proton synchrotron. And again, the accelerator worked very, very well, and this culminated recently with the construction of the Large Hadron Collider, also at CERN, and this is yet a bigger circular accelerator with a radius of nearly 10 kilometers. So another tenfold increase on the size, on the radius of this circular accelerator. So while these accelerators are extremely successful, it's somewhat clear that there is a limit to the size that these accelerators can take. And this has been acknowledged. For example, Burton Richter has written that without some transformational developments to reduce the cost of the machines of the future, there is a danger that we'll price ourselves out of the market. And it is exactly at this point where plasma accelerators can come into play, because they can be much smaller than conventional accelerators, and hopefully also much cheaper. So the typical sizes of plasma accelerators, they are getting progressively longer, but still they started with 1 millimeter accelerator, and hopefully to reach the energy frontier, 100-meter plasma accelerator would be needed. But these scales are still much smaller than the typical scales of a conventional accelerator. How does this work? So plasma accelerators were first proposed in 1979 by Toshiki Tajima and John Dawson. They proposed the concept with theory and simulations only, and the concept relies on electrostatic plasma waves in 1D. This was how the concept was first illustrated. So it uses probably the simplest mode of all in plasma physics, electrostatic plasma oscillations in 1D. So these are electron density perturbations. These electron density perturbations have a certain wavelength and thus a certain wave vector, and they typically oscillate at the plasma frequency. And associated with these electron density perturbations, there are also electric fields, very strong electric fields that can be used to accelerate particles to high energies. So in order to estimate the electric fields present in a plasma accelerator, we can do very simple calculations. For example, starting with the Poisson's equation, we take the Fourier transform of Poisson's equation. So here, E is the elementary charge, N0 is the plasma density, epsilon 0 is the vacuum permittivity, K is the wave vector, E is the typical electric field that we expect to find. So now, in order to estimate this typical electric field, we can combine the Poisson's equation with the dispersion relation. So K is equal to the frequency divided by the phase velocity, the frequency being the plasma frequency, the phase velocity being close to the speed of light for providing efficient electron acceleration. And if we combine all this together, we get this scaling law for the typical electric field inside the plasma accelerator, which tells us that the electric field scale with square root of the plasma density, of the plasma electron density in units of electrons per cubic centimeter. And this comes in volts per centimeter. So now if we just plug in typical numbers for the density in a typical laboratory plasma with an electron density of 10 to the 18th electrons per cubic centimeter, then this gives us an electric field of the order of a gigavolt per centimeter. And this is much higher than the typical electric fields inside the conventional radio frequency accelerator, which is on the order of 100 megavolt per meter at most. And so this is the fact that these extremely high electric fields provide the main motivation underlying plasma-based accelerator research and their applications. So the concept that, as it was first proposed in the paper by Toshiki Tajima and John Dawson, was extremely simple. It relied on an intense laser pulse that would propagate into plasma, into a gas jet. So the laser pulse was very intense, so it would ionize the gas, turn it into a plasma, excite these electrostatic waves inside the plasma, and then at the end of the plasma, there would be a relativistic electron beam being accelerated. So now the issue is that by the time when this idea was first proposed in 1979, the laser intensity was just barely above what was needed to ionize a gas. So we had to wait a little bit until the invention of the chirped pulse amplification technique that gave the Nobel Prize to Donna Strickland and Gerard Mourou in order to be able to increase the laser intensity beyond the limits that are needed to ionize the gas and also excite these large amplitude plasma waves to accelerate plasma electrons. And so this is an example of an electron spectrum that was obtained by one of these early plasma accelerator experiments. So this shows the electron distribution. The vertical axis shows the number of electrons that were measured as a function of their energy in a spectrometer. And so we see that these plasma accelerators, these initial plasma accelerators would accelerate electrons with a few hundreds of mega electron volts. Here in the bottom, we can see the typical divergence of these beams that at the time were of a few degrees. So now, then, at some point, something interesting started to happen. People call this the dream beam. So essentially, there were several experimental groups around the world that could drastically improve the outputs of these plasma accelerators. So the experimental setup was very similar to before. In some cases, the only thing that had to be done was to increase the plasma density a little bit. And once people did this, the energy spectrum of this electron bunch changes completely. And they started to show some quasi-monoenergetic features. So isolated electron bunches with narrow energy spreads or narrower energy spreads. So these are the first three spectra of these electrons obtained at Berkeley, at Imperial College, and also at LOA. And so they all show electron bunches with a few tens of megaelectron volts to a few hundreds of megaelectron volts. And they all show that now the energy spread is now relatively narrow, of a few tens of percent in comparison to the broad energy distribution that of before. So this was a major achievement that has triggered research and development of very high power, much higher power laser pulses around the world, in Europe, in the UK, in France, and at the extreme laser infrastructure, just to give a few examples. And so now using these much more powerful lasers, today and recently, laser plasma accelerators were able to accelerate 10 GeV class quasi-monoenergetic electron bunches in a plasma with a length of 12 centimeters. So these are recent experimental results obtained in 2024, last year, and they show clearly these monoenergetic features at energies which are much higher, of approaching 10 gigaelectron volts. So the progress has been tremendous, and this led to the so-called plasma revolution, which was only possible because it leveraged a triad of theory, experiments, but also simulations. So numerical simulations have been playing a very important role in the development of plasma accelerators, and they are only possible because there has been, so in par with laser developments, there have also been a tremendous advance in computing power over the years. And so because of this high computing power, supercomputing power that we now have available, we can exploit this computing power to model the plasma from first principles and predict the outcomes of these plasma accelerators even before the experiment takes place. So computer simulations are faster than building an entire experiment. They are also cheaper. So they work as a virtual laboratory to test new ideas and to design and predict the outputs of experiments. So there are many types of simulations that can be done, but perhaps one of the most famous methods that is used worldwide is the so-called particle-in-cell simulation technique. And this technique really enabled groundbreaking advance. So the trick that allows these simulations to actually be performed is that the space is divided into a grid, and there is electric and magnetic fields that are defined at the grid points, and particles communicate with each other through these electric and magnetic fields that are defined in this numerical grid. So this lowers the computational cost to something that goes nearly proportional to the number of particles in the system, which is much, much smaller than the computational cost of molecular dynamics simulations, for example, where it scales with the number of particles squared. And here the trick, or the trick really is that particles communicate with each other through the electric and magnetic fields that are defined in this discrete grid. So here on the right, we have a typical loop of a particle in cell, of a standard particle in cell code. So we start by having some electric and magnetic fields that are defined in this numerical grid. And then we interpolate these fields into the positions of the particles. So particles can move around in this grid more or less freely. So once we have the electric magnetic fields at the particles' positions, we can compute the force and advance the particle position using the fully relativistic Lorentz force. And once the particles' positions and velocities are updated, then we can deposit their currents back into the grid and use the currents in order to advance the electric and the magnetic fields using a discretized version of Maxwell's equations. And then we return to the first point, and this concludes a single particle in cell time step. So now if we repeat this loop over and over again, then we can advance the plasma over time and predict its self-consistent evolution for longer times and propagation distances. So at IST, we have been developing the peak code OSIRIS. This is a massively parallel and fully relativistic peak code. It has been developed in collaboration with UCLA and now many other institutions, for example, Michigan. And so this movie here will show an example of a particle in cell simulation of a laser wake-field accelerator. So we'll see here these colors, these blue and red colors is the electric field of a laser pulse. The pulse is moving to the right. The transverse axis is the transverse direction. And here this simulation is done in a moving window. And this window moves at the speed of light. We are still going to see everything in the lab frame, but we are just moving it. We are just moving our window at C, such that the laser pulse will appear to be almost still in this frame, and we'll see the plasma flowing from the right to the left. So we'll see the plasma density in colors, in grayish colors. So let's see what happens as this laser goes, intense laser goes through the plasma. So this laser exerts a radiation pressure over the plasma. This radiation pressure pushes plasma electrons radially until forming this nonlinear plasma wave that we see here. So white means void of plasma electrons, dark colors means higher concentration of plasma electrons. So at the back of this nonlinear plasma wave that we see here with this relatively complicated shape, the electric fields here at the back are very strong, and they can spontaneously trap plasma electrons from rest and accelerate them to relativistic energies in a short distance. So we see a fraction of these accelerating electrons. These are the colored streaks. They're colored according to their energies. And we see that their color changes from this purple color to red color, which means that they are gaining energy. So in this case, they go up to 40 MeV, just a few microns, just for an illustration. So this is already quite interesting, but we see that the physics is very rich. At some point, we see that these electrons that are injected trapped and injected into the plasma wave here, they at some point they start to drive their own plasma wave themselves at this point, for example. And even more, we see that in addition to their acceleration, these electrons also perform these transverse oscillations. They are called Betatron oscillations, and they are interesting because as electrons perform these oscillations, they emit radiation. And so this brings me to the plasma accelerator light sources. So before going into be a little bit more specific about how plasma accelerator light sources work, let me first remind the principles of how a conventional light source works. For example, for the case of a free electron laser. So free electron lasers provides the brightest X-rays that have been produced on Earth. And they have two main blocks which are important. The first one is an electron accelerator, typically accelerating electrons up to a few tens of gigaelectron volts, for example. And then this electron bunch is sent into an undulator magnetic field where this electron bunch executes transverse sinusoidal oscillations as it propagates, and as electrons perform these transverse oscillations, they emit X-rays, a lot of X-rays. And this is exactly what happens inside the plasma accelerator as well. So electrons are accelerated, and as they accelerate, the plasma wave also contains transverse electric and azimuthal magnetic fields that bend particle electron trajectories and make them oscillate, making these sinusoidal oscillations. And since particles are traveling mostly in the forward direction and they are feeling an acceleration which is perpendicular to their main direction of propagation, they emit radiation. So typically this mechanism leads to the emission of X-rays. So now let's have why is this even important? So why do we care about light sources at all? So light sources, and specifically X-ray sources, are quite important in a number of fields. And this is just a few examples. For example, archaeology. So this is an image of a piece of land that was imaged by an X-ray beam that allows to see some features inside this piece of land without destroying it. It's also important for non-destructive testing of materials. Of course, we all know medical imaging, X-rays of the human body to detect and diagnose some issues, and even then important for the treatments. They are also important for the imaging of circuits. So, for example, for the design of the next generation of computer chips. And they also play an important role to image high energy density states of matter, which is important in fusion, for example. So this is an image produced by an X-ray beam that shows the energy flow in fusion experiments at NIV. So light sources are quite important. So now let's look a little bit more, try to have a more intuitive picture of how radiation is produced as relativistic particles perform this sinusoidal oscillation. So this movie will show us this intuitive picture. So it shows the motion of a highly relativistic charged particle undergoing a helical motion. It's the same thing, helical or sinusoidal, from the point of view of the generation itself. So the particle starts to produce this radiation burst. We see the radiation here being produced. The radiation is collimated. It has an aperture of 1/gamma. And the pink rings here, they are the radiation that is being produced. So now we see that this radiation burst that is being produced is much shorter than the typical wavelength of the electron oscillations. So we really need to zoom this in order to be able to see the radiation wavelengths, which are usually gamma squared times smaller than the typical oscillation of the electron. And now this radiation can be detected or used somewhere outside the acceleration in a detector, for example, as in this case, from a computer simulation. So now the physics is quite rich. It has a few more details. For example, radiation is emitted in every angle. So every direction, there is radiation in every direction, although it's predominant mainly in the forward direction. And usually, as electrons perform these sinusoidal oscillations, they emit several wavelengths, harmonics. Several harmonics are being emitted simultaneously. So this image here shows the harmonic spectrum associated with sinusoidal oscillations of a relativistic electron bunch. So in the vertical axis, we see the frequency. horizontal axis, we see the emission angle and the different harmonics. So essentially, we see that the frequency drops as we move away from the direction of propagation of the electrons. So these are some of the basics of undulator radiation, which is crucial for to understand this Betatron radiation, plasma accelerators, or undulator radiation in free electron lasers. So because this radiation is, the wavelength is extremely short, it's also challenging to capture this radiation, particularly in cell codes, because simulations, they are usually good at resolving the particle motion, so the resolution is good to resolve the motion, the scales associated with electron motion, but the radiation that is emitted by these electrons is much, much shorter than the typical wavelengths associated with electron motion, typically gamma squared times shorter. And while the peak simulations could be done to capture this radiation, computationally, this would be unbearable. So I don't think there is the possibility to do simulations at the moment, at least in the laboratory frame. So we then use a trick to capture this radiation using these linear Vickers potentials, which allows us to capture the radiation emitted by relativistic electrons without actually increasing the resolution of the peak simulations. And we can do this at the simulation runtime using the quantities that are available inside the particle in cell loop. So the acceleration of the electron, the velocity of the electron beta, and also as a function of the direction of the emission direction n. So this is, we implemented this in OSIRIS, and we called it the radiation diagnostic for OSIRIS, or radio in short. Okay, so now there are many ways to use plasma accelerators to power light sources. One of them is to combine a plasma accelerator plus an undulator. So we replace a conventional accelerator in a free electron laser by a plasma accelerator. So the operating principle of this scheme has been demonstrated. The technology is still under development, but this is going to be employed in user facilities, such as for the Eupraxia facility. Now, if you would like to make this a little bit shorter, then we could replace the magnetic undulator by an optical undulator. So we would scatter the relativistic electrons in the fields of an intense counterpropagating laser pulse instead. So this is the basis for the nonlinear Thomson or Compton scattering. This typically provides very high energy photons, much higher than in a conventional undulator, because the undulator period associated with the laser is much shorter than the undulator period of an undulator, of a magnetic undulator. So this gives rise to MEV to GeV photon beams, which are useful to probe strong field QED, and could also become important in photon-photon collider concepts, for example. And if we want to make this the simplest configuration of all, this is an all plasma-based light source. This is the typical Betatron radiation source that I've shown earlier. So the radiation here is intrinsically broadband, so many harmonics are emitted at the same time. Photons are produced with a high energy from keV to MEV, and has the advantage that the X-ray emission is intrinsic to the acceleration process. So it's a relatively simple mechanism from an experimental perspective, at least. So now Betatron radiation has been used for several applications. For example, to probe high energy density states. So here Betatron radiation was used to probe a shock, a laser-driven shock in a solid target. It has also been used to provide tomographic reconstructions of biological samples with extremely high resolutions. So here at the middle, we see a tomographic reconstruction of a bone sample, And here on the right, we see the reconstruction of an embryo of a mouse, for example. So all this was done using Betatron radiation in the laser wake field accelerator. So now how does this Betatron sources compare with all other sources that exist and have been used? So this is shown here in this plot. So it shows the peak brightness of several sources that are available as a function of their energy. And I want you to focus on Betatron sources here, and this is the black dashed line. And here above, there is the free electron laser. And so the important part here is that the brightness of Betatron sources is nearly 10 times orders of magnitude below the brightness of free electron lasers. And the main reason is that the emission in Betatron sources, they provide the temporal incoherent emission. So every electron emits out of phase with respect to each other. And so the resulting interference is not completely constructive. Whereas in the free electron laser, there is constructive interference of the radiation of every electron. And so this really boosts the peak brightness. Now, if we were able to make Betatron radiation temporally coherent, then we would be able to bridge the gap between the brightness of current Betatron experiments and the FEL and reach the brightness of a free electron laser. And suddenly, Betatron sources would become competitive with respect to free electron lasers in terms of the peak brightness. And so the question that we're trying to address is, can plasma accelerator-based light sources actually become temporally coherent and also superradiant, so emit a lot of radiation? So before giving our perspective on this question, let me remind what happens inside the free electron laser. So this plot here shows the radiated energy as a function of propagation distance of an electron as an electron travels through an undulator magnetic field. So at the beginning, every electron radiates out of phase with each other. Radiation is incoherent. And as a result, the radiated energy or intensity is proportional to the number of particles inside our electron bunch. But then something interesting starts to occur when this electron bunch starts to self-consistently interact with the radiation that it's producing itself. So when the quality of this electron bunch is sufficiently high, then this bunch starts to be microbunched at the radiation wavelength. And eventually this microbunching, the so-called microbunching instability or free electron laser instability, forms a train of electron microbunches, and every electron in each microbunch radiates in phase with its neighbors. And because of this, the radiation from different electrons interferes constructively, and the intensity of the radiation then scales with the number of particles in the microbunch squared. So this is the typical scaling underlying superradiant emission, which is typical of superradiant free electron lasers, which can achieve the brightest X-ray beams of all sources. So now our take here is to use collective effects to achieve this, to bridge the gap and go from incoherent emission to coherent emission and superradiance. So actually, this is interesting because collective effects are already critical to advanced light sources, although we are usually not used to thinking we're not used to think like this. So let's just remind what happens inside the free electron laser. So we initially have this electron beam. All electrons are scattered, and they are producing their own X-rays, and their superposition is not fully constructive. But after the free electron laser instability takes place, we have this microbunching, and then every electron inside each microbunch emits in phase with respect with each other, and as a result, there is constructive interference of the different rays emitted by every electron. So here in the free electron laser, every microbunch emits like a single finite-sized particle, a single finite-sized giant electron that emits coherently. This is a very simple, plus the simplest example of a collective trajectory where the collective trajectory and the single particle trajectory are exactly the same. But there are many other light-emitting systems where these trajectories are completely decoupled from each other. And here we want to explore this freedom in order to bring superradiant emission to plasma-based accelerators. And so, I mean, collective effects they are ubiquitous in plasma. In fact, plasma physics is all about collective effects. Even in plasma accelerators, they are very common. For example, in instabilities like the self-modulation instability for the awake experiment or the Hosing instability. This is also a collective manifestation, the collective effect inside the plasma. But perhaps the simplest one of all are just simply nonlinear plasma waves in a usual laser wake field or plasma wake field accelerator. So these nonlinear plasma waves, they do exist. They have been measured experimentally. Their fine structure has been measured. And they also radiate. So here we see an image of the radiated power from a nonlinear plasma wave. And so most of the radiation is emitted here at the back of the plasma wave by this dense electron spike that is formed. Let's call it a super electron. And then this super electron actually produces most of the radiation of a nonlinear plasma wave itself. So this is more or less analogous, if you like, to this giant C wave, which plays the role of a nonlinear plasma wave. Then we have the crest of the C wave. This would play the role of this dense electron spike, this super electron. And then we have all this foam, which would be the radiation being emitted by this nonlinear plasma wave. But now we are going to think about this super electron as a finite-sized particle. And you can actually show theoretically that this super electron, this dense electron spike, radiates as a finite-sized particle, which we can also call a quasi-particle. And so if we think in this perspective, this can lead us to new radiation behaviors in plasma. So this is interesting because now these quasi-particles, they have unrestricted trajectories, velocities, and accelerations. And so they can travel arbitrarily fast, they can be subject to arbitrary high acceleration, and this is because they are a result of a collective effect. Okay, so we don't break any type of physical law. But still, this can bring us new radiation mechanisms that would be forbidden to single electrons, because, for example, single electrons cannot travel faster than the speed of light. But the collective effect can. There is no issue. And hopefully this can enable temporal coherence and bring superradiance to plasma-based accelerators. And this would be really exciting, a really exciting accomplishment. So let me now show you an example of such a superluminal quasi-particle in a plasma accelerator. So we are going to have to propagate an electron bunch, a 10 gig electron volt electron bunch, same thing for a laser pulse. It's going propagating into the right. Again, this is in a moving window. This electron bunch is going to propagate into a plasma density up ramp. And here at the bottom, we are going to see a waterfall plot that will allow us to see the trajectories of these quasi-particles, of these super electrons, as the driver goes through the plasma in a co-moving frame that travels at c. Okay, so you see here this first nonlinear plasma wave. We have this first quasi-particle here, this dense electron spike here at the back. And now as this electron bunch propagates, we see that these super electrons, these quasi-particles, they move forward with respect to a frame that travels at the speed of light. So these are superluminal quasi-particles. So here we see the velocity agrees quite well with the theory for the first three quasi-particles, the first, then the second, and finally the third, and there are others. So these are superluminal effect, but this is like the Mexican wave in a stadium. So in a Mexican wave, actually people are still, they just move up and down, yet there is an effect that travels transversely. The wave travels transversely to their oscillatory up and down motion. And the same thing here. So electrons individually, they travel at a subluminal speed, but collectively, there is a collective effect that is superluminal. So so now we are ready to capture the radiation using this radiation diagnostic for OSIRIS. And this brings us to this quasi-particle Cherenkov superradiant emission. So it's a scheme that can lead to broadband, single cycle, off-axis photon bursts, relying on these optical shocks that are produced by this superluminal source of electrons. So usually you cannot do this in vacuum for a single electron because no single electron can travel faster than the speed of light, but we can do it if we use quasi-particles. So here on the right, we see an image of the radiation intensity in a detector from a simulation placed in the far field. So in the horizontal axis, we see the angle of emission, and the vertical axis is the time, the detector time. And so we see these three bright bursts of radiation at these three different angles. And these three different angles, they coincide exactly with the Cherenkov angles associated with the velocity of the first, the second, and of the third quasi-particle. So you see the emission, this is a very short, ultra short light burst. It's a single cycle light burst. So this is a zoom in of one of these radiation bursts that is being emitted. This is the intensity. It's a single cycle burst. And if we take the Fourier transform, then we see it's broadband. We can also track the evolution of the peak intensity as a function of propagation time. It's superradiant. I mean, it's a quadratic increase. There is a quadratic scaling, which is the typical superradiant scaling. In this case, it means that the intensity grows quadratically with the number of particles that is participating in the process. So now this is an example of this quasi-particle coherence or superradiant quasi-particle emission, broadband. We can also make it narrowband through this quasi-particle undulator radiation. So in this case, we need to make quasi-particles to undulate like in a conventional undulator. And we can do this by using a corrugated plasma density profile as shown here in this panel. So if you use this type of density profiles, then we see that the quasi-particle here at the back, the superelectron is wiggling back and forth. So in an undulator, the oscillation is transverse, but here the physics is going to be very, very similar. So we see this undulating motion of these electron spikes. Now these corrugated plasma channels, they can be produced, and they have been produced in the laboratory thanks to the superposition of different lasers coming at different angles, ionizing the plasma, and then leading to this type of structures. So now we can compute the radiation. This is the spectrum of the radiation that we get. And suddenly we start to see these different undulator harmonics that I've shown to you a couple of slides before. So we see these different harmonics being emitted by these undulating quasi-particles. This is for a subluminal quasi-particle, as if it would be an electron. And of course, this undulator radiation is impossible when the electron is superluminal. But now if we use quasi-particles, we can make them superluminal. And this is how now the superluminal undulator radiation spectrum turns out to be. So it is a mixture between Cherenkov emission here at this angle with conventional undulator radiation. And we can even make it more superluminal, so we start to see more features here for smaller angles. So these were examples using a plasma wave field, so an electron beam driver to excite the plasma wave. But we can get essentially the same physics in a laser wave field accelerator. So this is an example. So it's actually a simpler example where the laser pulse goes into a linear plasma ramp instead of being a carefully tailored plasma ramp. This is just a linear slope. So the density increases linearly with the propagation distance. Here at the bottom, we see the first and the second quasi-particles. They are propagating at a relatively constant speed. And here is the radiation spectrum. So we see this Cherenkov, quasi-particle Cherenkov radiation here at the Cherenkov angles for the first and for the second electron density spikes, which evidence that this effect can also take place in the laser wave field accelerator. So interestingly, the simulations also capture the radiation emitted by the electrons as they interact with the laser. So this is the emission. This is the emission of these electrons at the fundamental frequency of the laser. This is at the third harmonic and even the fifth harmonic. And what's interesting here is that this quasi-particle radiation is stronger. The intensity is higher than for the third harmonic, for example. So in principle, this radiation can be measured in experiments. It's sufficiently bright to be measured in experiments. Okay, so now we can actually provide an estimate for the brightness of this source of radiation, and the typical radiation energy, the typical photon energies can be tuned quite easily, for example, by changing the plasma density. So this gives us a huge flexibility, and we can have a huge control over the ranges of frequencies that are being emitted. So if you use lower plasma densities, for example, on the order of 10 to the 16th, then we can have the emission of terahertz. And then as we increase the plasma density, we go to the ultraviolet. And in the limit, we could go to 10 to the extreme ultraviolet. So now, this is an image that shows that the peak brightness or peak brilliance of different light sources, also operating along a range of energies. And now this is where, in principle, this quasi-particle radiation concept could be. So it would emit the same brightness of a free electron laser operating in the same energy range. Okay, so now let me just conclude the talk. So I've provided an overview of plasma-based accelerators. They now provide for compact and high-quality electron bunches. They are ready to be used in free electron laser, for example. And here it's very important to rely on this triad of experiments, theory, and simulations to progress. Now, plasma accelerator light sources have many applications, including imaging of high energy states of matter, imaging biological samples with unprecedented resolutions. And I've also shown an advanced concept to obtain superradiant emission in plasma-based accelerators based in this quasi-particle light source concept. And yeah, so this is it. Thank you very much.
Thank you very much to Professor Vieira for such an engaging talk. We have got a couple of questions, so if it's okay, I will go ahead with those. So the first question for you today is, in plasma-based accelerators for FELs, electrons undergo betatron oscillations. What physical or engineering strategies have been developed to mitigate the negative impact of betatron oscillations, such as emittance growth and unwanted radiation, while preserving or even enhancing the beam quality for FEL applications?
Okay, so thank you for the question. So let me try to move earlier to a more relevant slide. Yeah, right here. Okay, so oops, my computer is a bit slow. Okay, so yeah, so the usually for the conditions of laser of the Betatron radiation from a laser wake field accelerator, the effects of the radiation in the quality of the electron beams is nearly negligible. So for typical conditions, at least as far as I'm aware, the influence of Betatron radiation doesn't really degrade beam quality. Effects like radiation back reaction would become important, but only in much more extreme scenarios of electron energies, focusing fields, and also amplitudes of the oscillation. It's possible that they play a role, but for much more extreme scenarios than the ones that experiments operate today. So this we can essentially neglect this effect for current experiments.
Okay, thank you very much for that. And another question. Are there experimental verifications of the quasi-particle radiation concept?
Yes, so there has been a recent verification in experiments. They did not use a nonlinear plasma wave. Instead, they observed the effect in an ionization front, so in a superluminal ionization front, and they observed precisely this ultra bright or very bright bursts of radiation at the Cherenkov angle associated with the velocity of the ionization front. So this was recently published in Physical Review Letters in the group of Emilien Hubbard and Vladimir Tikhonchuk. I'm sorry, I cannot pronounce the names very well. But yes, so there has been some early experimental verification, not of the concept using nonlinear plasma waves, but of the concept using superluminal ionization fronts. But the physics it's the same.
Okay, thank you very much. I think we might have one more question. If you could just pop it in the chat, please, so that we can read it out. I think I can see someone's got their hand up. If you could just quickly type it out, then we can put it to our speaker. Okay, we'll just wait a second to see if it comes through. Okay. So the question is, what are the prospects of superradiant quasi-particles in terms of applications?
So the type of applications that one can envisage for quasi-particles would be, for the undulating quasi-particle example, for example, would be similar to a free electron laser, to what the type of applications that are appropriate for a free electron laser under the same energy range. Now, one interesting thing about the broadband, for the superluminal quasi-particle, is that the emission is broadband, and it's nearly a single cycle, and so it's very short. And even a free electron laser, so usually even free electron lasers, the radiation that usually comes out from a free electron laser is not a single cycle radiation burst, light burst. It's a sequence of X-ray. I mean, it's a train. I mean, it's just a sinusoidal X-ray beam. So where electric fields, there's many electric field oscillations there. But here in this regime, the emission is just a single cycle. So it's ultra short, and in principle, this could open up the possibility also to probe dynamics at these extremely short durations. And so this would be an interesting application. I mean, if this would be verified experimentally more broadly, is to use this radiation to try to image, for example, chemical or molecular processes that occur at very short time scales using these ultra short pulses of radiation.
Okay, thank you very much for that. So I'd just like to say a huge thank you to Professor Vieira for giving up his time today and for carrying out our first talk in our Eupraxia seminar series. Just as a reminder to everyone, we will be hosting these webinars around once a month going forward. So the next one is going to take place on Friday, the 13th of June. We've got our speaker lined up. So it is Dr. Joseph Wolfenden, who is part of the Quasar group at the Cockcroft Institute. And he's going to be talking to us about beam diagnostics. So if you're already registered for the seminar series, that's great. Some information will be sent around to you soon. But if not, then keep an eye out. You'll be able to see an abstract and some more information about his talk. So thank you all very much for attending today. I hope you have a nice rest of your day. And thanks again to Professor Vieira.
Thank you.